Jai Hind everyone. My name is Dr. Dibya Bharti. Today I am going to discuss transient circuit analysis with subject KEC 303. Subject name is network analysis and synthesis. In earlier lecture also we had discussed the transient analysis, but for the circuit of RL and RC network only. So today we will discuss transient circuit analysis with the circuit RLC. That means there will be resistor, inductor and capacitor. So also we will see some of the examples. So how to analyze this RLC network for transient analysis. So these are the contents of the today's discussion only. So we will first see the transient response of RLC circuit and we will take example of series RLC circuit. Then we will solve some of the numerical problems also related to the transient response. So here a series RLC network has been considered here. Okay, so we had seen the concept of switching in earlier lecture. So when switch is closed at time t equal to 0, the current IT will be flowing. Here V is the voltage that will be connected to the circuit elements R, L and C when switch will be closed. So now it has been mentioned here that capacitor and inductors are initially uncharged. That means there is no current through the inductor and there is no charge over the capacitor when we are closing the switch. Okay, so when circuit is closed, the current IT will start flowing. So if we apply the KVL, that is Kirchhoff's voltage law, for t greater than 0, then we can write the equation. We can write this equation. Okay, so here we can write this equation, that V equal to Ri, V minus Ri minus L di by dt minus 1 by C integration I dt. Okay, is equal to 0. Ri is the voltage drop across the resistor, L di by dt is the voltage drop across the capacitor, and 1 by C integration I into dt. Okay, so we are taking integration for time 0 to t. So this is the KVL equation when we are closing the switch. Now if we differentiate this equation, see, this equation is not the differential equation, this is the integral differential equation because integration part is involved there. Okay, so to solve this equation, we will first convert this into the form of the differential equation. Okay, so for that we need to do the differentiation again for this equation. So if we differentiate this equation with respect to t again, so V will be the constant, so this part is 0, R di by dt, L d2i by dt square and 1 by C I. Okay, so now integration is not there in the equation. So by rearranging this equation, we can write this as, so we can write this as L d2i by dt square, okay, d2i by dt square plus R di by dt plus 1 by C into I. This is equal to 0. Okay, so now if we divide this with L, we will be having this equation. Okay, so d2i by dt square plus R by L di by dt plus 1 by LC into I. So now this is a second order differential equation. Okay, so the auxiliary equation or the characteristics equation of the same form of the second order can be written as S square plus R by L into S plus 1 by LC. Okay, so if we take, or we can say that di by dt as S. Okay, so then the auxiliary equation of this can be written as S square plus R by L into S plus 1 by LC equal to 0. Or we can write this as d square, okay, plus R by L into d plus 1 by LC equal to 0 also. Okay, if we do the analysis in time domain, we can assume di by dt as d and then we can write this equation also. Okay, so but here we are taking equation in terms of S. So the auxiliary equation has become S square plus R by L into S plus 1 by LC. So now since it is a quadratic equation of S, so there will be two values of the S and we can denote that with S1 and S2. So the roots of the equation will be given by minus R by L 2L, or we can write minus R by L plus minus R by L square minus 4 by LC, okay, divided by 2. This whole divided by 2. So S1 and S2 will be minus R by 2L plus minus R by 2L square minus 1 by LC. So these two are the roots of the auxiliary equation. So now we can write this as minus alpha plus alpha square minus omega square, and second one is minus alpha square minus omega square ka square root. So now here alpha is the R by 2L and omega is 1 by under root LC. Okay, so if we assume this alpha square minus omega square as beta, we can write this beta as under root alpha square minus omega square. So these are the equations. So now the solution of the above differential equation, that means solution of the equation, we can write this as it equal to k1 e to the power s1t plus k2 e to the power s2t. Okay, so S1, value of the S1 and S2 are, we can derive this minus alpha plus beta minus alpha minus beta, and the value of alpha and beta are written over here. So the solution has become k1 e to the power s1t plus k2 e to the power s2t. Here k1 and k2 are the constant. Okay, so and S1 and S2 are the roots of the equation, roots of the differential equation, that is minus R by 2L plus minus R by 2L square minus 1 by LC under root. So now depending upon the values, see the value of the S1 and S2 are depending on the values of R, L and C. So depending on the values of R, L and C, we will be having the three cases for the responses. Okay, so basically this IT the response. Okay, IT was the output of the circuit. See here, output, okay, V was the voltage as the input and IT is the current that is being flown after connecting voltage source. So we need to calculate the IT. IT is the response or the output. So here IT is the K1 e to the power S1t plus K2 e to the power S2t, and the values of the S1 and S2 are depending on the values of R, L and C. So we will be having the three cases. Okay, so see here, if the value of alpha is greater than omega, second one is the when value of alpha is equal to the value of omega naught, and third one is the when value of alpha is less than value of omega naught. So first case is that when value of alpha is greater than the value of omega naught. So here if value of alpha is greater than omega naught, that means R by 2L is greater than 1 by LC. So R by 2L is greater than 1 by under root LC. So in this case there will be two real and unequal roots. Two real and distinct roots will be there, and this condition is known as the overdamping. So this is the overdamped response. Okay, so in this case the solution will be e to the power, IT will be e to the power minus alpha t. Okay, so I will be e to the power minus alpha t, K1 e to the power beta t plus K2 e to the power minus beta t. Okay, so this is the solution for the case of overdamping when R by 2L is greater than 1 by under root LC, and this is the curve. Okay, so this is the curve for the overdamping. This is IT has been plotted here with respect to time. So second one is when alpha is equal to omega naught. Okay, that means R by 2L is equal to 1 by under root LC. Okay, so in this case roots are real but they are equal. Okay, so this case is known as the critically damped situation. Okay, so first one when alpha was greater than omega naught, that was overdamping case, and here when alpha is equal to omega naught, this is the critically damped situation. Okay, so in this case current I is e to the power minus alpha t, okay, K1 plus K2 into t. Okay, so now this is the curve for the curve of the current for critically damped situation. Okay, so now third one is the under damped response case when alpha is less than omega naught. Alpha is less than omega naught, that means R by 2L is less than 1 by under root LC. Okay, so in this case roots are complex conjugate of, okay, so two roots S1 and S2 are complex conjugate of each other. So and this gives the under damped situation. Okay, so see this type of plot is there. So the plot has been, okay, so this condition is the under damped situation. Okay, so here solution, that means response IT is K1 e to the power S1t plus K2 e to the power S2t. Okay, so S1 and S2 are minus alpha plus minus alpha square plus omega square. Okay, so here alpha square minus omega square will be there. So S1 and S2 are minus alpha plus minus alpha square minus omega naught square. Okay, so here let us assume that this alpha square minus omega square, since value of alpha is less than omega naught, okay, so it will be complex number. So minus alpha, and we assume that this has omega d, so it will be j into omega d. So now omega d, value of omega d, here omega d we can write this as omega naught square minus alpha square. See now, so IT will be e to the power minus alpha t K1 e to the power j omega dt plus K2 e to the power minus j omega d into t. So now we can write this as e to the power minus alpha t K1 plus K2 e to the power j omega dt plus e to the power minus j omega d into t divided by 2. Now plus j K1 minus K2 e to the power j omega t minus e to the power j omega dt divided by j into 2. So we had written this equation in term of omega d. So now we can write this as e to the power minus alpha t K1 plus K2 cos omega d into t plus j K1 minus K2 into sin omega d into t. So what we had assumed that omega d is omega square root of omega square minus alpha square. Okay, so this is the situation of under damping. So now this is the example that in the network shown. Okay, so three cases we had discussed. In case of series RLC network, first condition was of the over damping when alpha was greater than omega. Okay, second one, when alpha was equal to omega, that was condition of critically damped, and when alpha is less than omega, that condition was the under damping situation. So here with the example we will all analyze the response, transient response in various circuit. So first is the, here in the shown network 5 volt voltage source is there. Okay, so here switch position may be at A and may be at B. So here resistor of 2 ohm are there. Okay, 2 resistors are there with value 2 ohm each, and 1 by 4 farad capacitor is there. So now it is mentioned in the question that the switch position is shifted to position B, okay, at t equal to 0. That means initially before t equal to 0, switch was at position A, and question is to find the value of Vt for t greater than 0. Okay, that means before t equal to 0, or we can say at t equal to 0 minus the switch was at position A. Okay, so when the switch was at position A, okay, when switch was at this position, this 2 ohm resistor was out of the network because this terminal is open. That means before t equal to 0, this 1 by 4 farad capacitor and this 2 ohm resistors are connected with 5 volt source. So now at t equal to 0 minus, that means before, when we are changing the position of switch from A to B, okay, the circuit was in the steady state condition, okay, that means the capacitor will behave as the open circuit. So here the capacitor is open and the 2 ohm resistor is there, okay, that means voltage capacitor was in a steady state, that means here the VC, this part VC is equal to this VC, okay, see, this VC is equal to 5 volt, okay, and the VC 0 minus again, so this VC 0 minus is 0 and is 5 volt, okay, this V0 minus is 0 and this capacitor has attained the steady value, that is of the 5 volt, and this 5 volt is equal to the source voltage. So now at t equal to 0, when switch position is at B, now the source 5 volt is out of the network and this 2 ohm resistor is connected. So now this capacitor, since this capacitor has attained a value of 5 volt, that is equal to the source voltage. So now this capacitor will now behave as the source, okay. So now current that is flowing after just connecting the switch, that is I0 plus, that is minus 5 by 4. 4 ohm resistors are there and this capacitor is now behaving as the source. So current I0 plus is minus 5 by 4, that is minus 1.25, and V0, okay, V0 plus is minus 1.25 into 2, so that is minus 2.5 volt, okay. So now this is the situation when we are connecting the switch from A to B. So for T now, third situation is that when switch has been at position 2B for T greater than 0, okay, not just after switching, okay. So when switch is at position B, after some time we will be having this 5 volt source and this 1.4 farad capacitor, these two resistors in the network. So now if we write the KVL equation in this situation, we can write this as 2I minus 5 minus 1 by C integration I dt minus 2I is equal to 0, okay. So now this is the in the form of integration, okay. So now we will differentiate this equation, okay. So now again we are differentiating this equation, okay, we are differentiating this equation. So this is minus 4 di by dt minus this 2i. So this is 4i and we are differentiating this. So it will be, this 5 will be 0, d by dt of 5. So now we are having this simple equation, okay. So now we will compare this equation with the standard differential equation, that is di by dt plus pi equal to 0. So here this p, value of p, if we compare this value of p is 1, okay. So the solution is I equal to k into e to the power minus p into t. So value of p is 1, so it will be k into e to the power minus t. That means the value of k is, if we put the initial conditions over here, the value of k will be 1.25. So it will be minus 1.25 e to the power minus t and vt will be this, okay. So this is the complete solution, okay. So now this is the second example, when in the shown network switch is opened at position at t equal to 0. So we need to calculate the voltage Vt. That means initially switch was closed. When switch was closed, this 10 ampere current source will be providing the current to resistors and the capacitor, okay. So now at t equal to 0 minus, see here, at t equal to 0 minus, and when the switch, before switch was opened, this capacitor has attained a steady value, okay. So that means voltage across the capacitor, this Vc0 minus is 0. So now if we write the Kcl equation at this node, Vc0 minus divided by Vc0 minus divided by 1 by 2. Okay, so these two currents. Okay, so suppose this current is being divided in these two parts. Okay, this is the open terminal. So V0 minus divided by 1, V0 minus divided by 1 by 2. This is equal to 10. So now we are knowing the value of the voltage before t equal to 0. So this is value is 3.33 volt. So now when the switch is open, okay, now switch is, this is the condition that Vc0 minus voltage across the capacitor will not change instantaneously. So Vc0 minus is equal to Vc0 plus, and this has been calculated as the 3.00. Now for t greater than 0, okay, so when t greater than 0, switch is open. So now this, if we can write the Kcl equation at this point, so it will be 1 by 2 dV by dt, okay, 1 by 2 dV by dt plus V by 1, this is equal to 0. So this is the equation, okay, this is the value of current, okay, so this is the value of current, 1 by 2 dV by dt plus V by 1, this is equal to 10. So now this is the differential equation. So if we compare and find out the solution, this value of P is equal to 2, okay, and this value of Q is equal to 20. So now the complete solution will be Vt equal to, now we are doing the calculating the integrating factor. So e to the power minus Pt, and it has been Vt equal to e to the power minus Pt integration Q e to the power Pt dt plus K e to the power minus Pt. So now if we put the values, we are having voltage equation as this, okay, and if we are knowing the value at the initial condition, so if we put t equal to 0, voltage is 3.33, okay, this is equal to 10 plus k, okay, if we put the value of t as 0. So now we can calculate the value of k, this as 6.66. So if we put the value of k, so complete solution is Vt is equal to 10 plus 6.66 into e to the power minus 2t. Okay, so these are the examples. So this is the third example, that in the given network switch is closed, okay, at t equal to 0. So we need to calculate the expression for the current. So this is the example of the series RLC network. R, L and C is there. When switch will be closed, we can write the equation. Okay, so when switch is open, okay, there is nothing mentioned in the question, okay, so we will not be able to calculate the initial values. So here when switch is open, we assume that current I and voltage, current through the inductor and voltage across the capacitor, this is 0, because nothing has been mentioned in the problem for calculating the initial values, okay. So when switch will be closed, I 0 plus and Vc 0 plus, this is also equal to 0, because current through the inductor and voltage across the capacitor don't change instantaneously. So now we can write the simple integral differential equation. So 20 minus 9I minus 1 di by dt, and this is the equation, this is integral differential equation. So we will what we will do, we will differentiate it and we will be calculating the values, okay. So two roots are there, so d1 as minus 4, d2 as minus 5. So here solution is it equal to k1 e to the power minus 4t plus k2 e to the power minus 5t, okay. So now if we differentiate this, this is the equation, okay. So now easily you can put the values of initial conditions and you can calculate the values of k1 and k2, because we need to calculate the values of the arbitrary constants, those are assumed here. So here if we are putting the values, this is the equation, okay. So this one and this one, these two equations are there. So now you can put the values, d by dt of I0 plus, this is 20, so this value is 20. Now by solving these equations, these two equations are there, and if we solve these two equations, we will be having the values of k1 and k2. So the complete solution it is this, okay. So this is the last example. So here switch is closed, okay, and steady state condition has been reached before that the at t equal to 0 switch is opened, okay, and we need to calculate the expression of the current. In similar way, when switch was closed, we will calculate the initial current through the capacitor, okay, and so this is initial current through the inductor is 100 divided this 100, okay, because this will behave as the short circuit, okay, this inductor will behave at the short circuit and capacitor will behave at the open circuit at a steady state. So current through the inductor is 100 divided by 10, that is 0, and voltage across the capacitor is 0. So now switch is opened. So when switch is open, okay, this is the condition. Now we had written the equations, okay, and this is the integral differential equation. So we need to differentiate it again, and we are having this equation, okay. We are now we need to calculate the arbitrary constants. So okay, we are putting the initial conditions, okay, in the equations, and we are calculating the values. So this is the complete solution here for the current. So these, see, the arbitrary constants are to be calculated with the help of the initial conditions, okay, or the initial values that we are having. We will put the value of t, okay, and then we will calculate the constants. So here this is the value of the current, okay. So this was the about the today's discussion about the transient analysis, and we had discussed today series RLC circuit for transient analysis. This can be very easily solved with the help of the Laplace transform that we will see in our next lecture. Thank you.